This is just very preliminary studies, so we didn't complete the spectra, and there are many simplifying assumptions. We just wanted to check the properties of some simplified dynamical systems. So this is not as advanced as Apostolos models or Yuri's and Boris model. So why I started to consider the situation. So some time ago, I was considering the formation of the kiloparsec scale halo in the host galaxies of BLX. So this is just a few slides to tell you why the simplified situation may be not that unrealistic. So previously, Aharonian et al. Considered the so-called the giant megaparsec scale halo around TV sources, extragalactic sources. So if you have a like BLX TV emitting AGN placed far away, then producing, let's say, 100 TeV photons, then those photons will be absorbed on the background fields, producing pairs. Those pairs will be isotropized in the intergalactic magnetic field, producing synchrotron and inverse Compton emission, and so the cascade, develops. So they discussed the case that even if the direct emission of the TeV BLX will be not observed because of Doppler hiding, for example, if this is like misaligned source, then there are some chances to detect the giant megaparsec scale halo around like cosmologically distant TeV emitting BLX. And in such a case, you basically absorb all of this primary emission and reprocess it and observe it at lower.
Sorry, what is the absorber? CMB or what?
No, so in this paper, they consider background photon fields. So CMB and EBL, so optical and infrared background, cosmic background, extragalactic background. This is, and therefore, they giant halos were like megaparsec size, right, for working for very cosmological distance. So I just was considering if something like similar phenomena cannot happen within the host galaxies of nearby objects, because we know, like we observe, typically BLX are hosted by giant ellipticals, so very evolved systems with only red giants, not much dust in the center. Actually, this is a picture of Centaurus 8 in optical, radio and X-rays, and this is like 4 kiloparsec, let's say here. So this is not that very typical because of this dust lane, because of the recent merger with some spiral galaxies. Typically, the host galaxies of BLX are really very empty systems. There is not much accretion density is very small. There are not much lines, not much dusty torus. So you have starlight, and we do observe TeV emission from those BLX. So we know that these systems cannot be like optically thick for TVs. But I asked the question: what is the TeV produced in the center has to propagate through the starlight? And we know the intensity of the elliptical powerful galaxies pretty well because of the Hubble Space Telescope. So we can quantify very precisely, and just to compute the optical depth and see how much of primary gamma rays emitted from the center will be absorbed in the host galaxy, and then what happens? And what happens if we absorb photons, of course, on starlight and in mid pairs, and we know that there is magnetic field in interstellar medium, so the pairs will produce synchrotron emission, and of course upscatter starlight to slightly softer inverse Compton. So that was in this paper, and just like this is the typical spectrum of elliptical galaxy, the starlight. This is the starlight of red giants, a little bit of dust. So so I carried the calculations, and what was interesting is that this is the typical frequency of the starlight photons, and typically we expect magnetic field in elliptical within 1 kiloparsec, few microgauss. So what is very interesting is that in this process, the synchrotron emission of the created pairs is almost the same for this magnetic field as this as the frequency of the soft photons annihilating gamma rays. So that was.
To calculate the rate, you need to know the photon field, right?
Excuse me?
To really calculate the rate, you need to know the photon field inside the galaxy.
Yes.
Right?
Yes.
But is it known well enough? I mean,
very precisely. This is one of the most precise, because you can this surface brightness of the starlight is measured very precisely by, for example, Hubble Space Telescope, from the very central region up to tens of kiloparsec scale. So we know surface brightness. And we know that elliptical galaxies are, virialized spherical system. So by integrating over the angles, we can estimate the energy density of the starlight photon fields. So that's actually So I just, at some point when I was doing this calculations, I was talking to John Kerr, and he pointed out that this is very actually interesting and can lead to some interesting effect that is the subject of this talk. But just to finish about this interiorization, for example, this is the optical depth calculated, and this is the scale. This is the optical depth. When you in units, this is the measure in units of the break radius for the surface brightness profile of the galaxy, host galaxy, Centaurus A host galaxy, which is 40 parsecs. And so if you produce TeV emission in the center, that would be the optical depth, and let's say 40 parsec, etc., etc. So it saturates at the level of, let's say, 0.01. So 1% of the TeV emission will be absorbed on starlight always.
This is for 2 TeV photon.
So yes, this is the optical depth for 2 TeV photons.
We occasionally see spectrum extending up to 15 TeV.
Yes, so no, I just that I just calculated. So optical depth, because of the photon annihilation cross section, the optical depth is the cross section is maximized for some particular frequency of soft photons, right, for given gamma rays. So let's say maximum of the starlight is emitted at this frequency, so that would absorb 2 TeV photons, right? So for all the other gamma rays, the optical depth would be lower. So this is like the maximum, right? For all the other gamma rays, the optical depth would be lower. And this is
but the number of infrared photons is smaller.
Yeah.
Yes.
In photon numbers, smaller.
Yes, I also calculated for the infrared, yes. And this is just to show on this axis the energy density of the starlight photon fields. So in the center, in the units of Earth per centimeter square, it can be noted that in a kiloparsec region of elliptical galaxies, the energy density of the starlight is order of magnitude larger than CMB. Orders of magnitude. So this is very interesting for any like inverse Compton emission in the jets. But anyway, just like we carry the calculation, so we inject gamma rays in the center of Centaurus A, absorb 1 photons, and then the point is that those created photon pairs will be isotropized in the interstellar magnetic field quicker than they lose energy. So therefore you form a giant isotropically emitting pair halo in a galaxy. So even though the primary emission can be Doppler hidden, this second, like this reprocessed emission, is isotropic. So that's something interesting, and this is just to keep the scale. So eventually, in the like stochastic acceleration for the photons in the host galaxy, the energy losses time scale due to synchrotron and inverse Compton emission here is for 2 different values of the magnetic field 1 and 3 microgauss, and this is the Klein-Nishina suppression and the escape. So we can say that TeV electrons, TeV energy electrons created in this absorption process, they are not very efficiently accelerated. They do not escape from the host galaxy, so they are really trapped within the galaxy where they lose all the energy. And they lose, of course, in this Klein-Nishina, mostly by the inverse Compton emission in the Klein-Nishina regime. And as a result, the cooled spectrum of those electrons deviate from standard cooled spectrum E2-2. There is this Klein-Nishina band, let's say. And this is for where I said 2 different values of the magnetic field 1 and 3 microgauss. So, as I said, this assuming, let's say, that the starlight is monoenergetic, and as was shown in the previous slide, this is a pretty good assumption. The energy, we are talking about like TeV energy photon are absorbed, creating TeV energy electrons. And just the last slide about Centaurus A is that in 2006 we calculated the spectrum of this pair halo. So this is synchrotron emission, this is inverse Compton emission for 1 and 3 microgauss. And Centaurus A was detected by egret. So these are the egret measurements of Centaurus A. So what we observed is basically this, but so this is the observed one, so this is Doppler hidden because the jet in Centaurus A is like 60, 50 degrees from our line of sight. So this is the observed D-beam emission. And we, for the calculated optical depth, so let's say 1% of the total radiated TeV emission that we just corrected for the typical Lorentz factor of the jet at standard, corrections. So the total radiated will be like this, and we absorb this emission, right, emitted by the jet in some, cone 1 over gamma of the jet, and that would be this isotropic emission from the halo resulting. And what is very interesting is that recently has telescope detected Centaurus A, as well as Fermi. So this is the Fermi spectrum compared to this egret spectrum, and this is Hess. And so this is exactly where we expect this, let's say, bump, and it's very interesting. So some people put doubts in the Hess measurement because they said that this is above extrapolation of the Fermi spectrum, but this is really what we expect from this halo. So, and the total luminosity in this is just as probably roughly here, just as we expected, and the spectrum can be probably fitted. This is really like simplified model, but it's I think that may be something in this. This is very interesting because this is a, let's say, calorimeter of the total gamma ray power emitted. And so coming back to the problem to the effect pointed out by John Kirk, so he said that it's very interesting because if we have a system, a magnetized system, into which we inject gamma rays, and as I said before, like this about Centaurus A was just to emphasize that in fact we can think about such a system. For example, a galaxy, right? We have magnetized interstellar medium, and we inject, for example, from the active center TV emission, some gamma ray emission. And so what if we start from like no opacity, there are no seed photons from the beginning, you just have magnetic field and we have TV, some gamma ray emission, and we perturb the system, just putting like, absorbing one photon, one gamma ray photon. That photon creates pairs, pairs emit synchrotron emission, and what if the magnetic field is such that the synchrotron emission of the created pairs absorb TV emission? So it's kind of resonance. And if you just, very roughly, the for a given energy of the gamma ray photon, the energy of the created electrons would be half this, and then the characteristic synchrotron frequency of this pair is given by the magnetic field intensity strictly. So that that would be the magnetic field needed. So there is a strong dependence on the photon energy, but what is interesting is that for a huge range of the magnetic field, from nanogauss to megagauss, so let's say astrophysical range, the energies of the gamma rays involved are in this range. So this is basically right now covered by Fermi and Cherenkov telescopes. So just to see the we wanted to check for which parameters of the source this process results in a non-linear production of electron-positron pairs, and therefore more and more absorption of gamma rays. So in order to do this, we just wrote the set of three equations. This is the number density per energy of the gamma rays, of the soft photons, and of the energy. So we inject gamma rays with some luminosity. For example, we have some luminosity like inert per second. We inject to the system. Those gamma rays escape and annihilate. And soft photons are created by the synchrotron emission of the created pairs and can escape from the system, while the electrons, they are injected due to photon-photon annihilation, and they cool due to synchrotron emission and inverse Compton emission. So this is related. So what we neglect here is, say, the gamma ray photon that we will have through this through inverse Compton emission is because we, to simplify the situation, we don't compute the spectra. We just compute the monochrome, everything for one frequency, like just one frequency of the gamma rays and corresponding monochromatic soft photon fields and monoenergetic electrons. So we do not produce more gamma rays in this process. Of course, if we would include somehow it when computing the spectra, there would be even more gamma rays, and the process would be eventually quicker. So this is the, for example, this is the number density. So this is like number of photons per energy per volume. So to look at the properties of this dynamical system, we may introduce some dimensional units for everything. And this is the set of equation dimensionless, let's say, and there are two only parameters that are controlling it. This is injection compactness, which depends on the size of the source, and injection luminosity of gamma rays, and this is the energy of gamma rays in the units of MEC squared. And magnetic compactness, which depends on the energy density of the magnetic field, size of the region, and again, the energy, which is related to the magnetic field as in the previous slides. So this is the standard definition of injection magnetic compactness, except of this energy here. So we just look standard analysis like a steady state, and so look, note that at the beginning there are no seed photons and soft photons and no electrons. Right? So we just in a steady state we just analyze the properties when you have a steady state solutions, if there are instability criteria, so very standard analysis. And to make it short, this is just a, let's say, final the results. So if the injection compactness is less than 3, there is only one steady solution, a stable solution, which corresponds to the that nothing happens. So you inject gamma rays, and even if you perturb it, so put just one one soft photon and create two pairs. This is the synchrotron emission created in this is not strong enough to do any interesting nonlinear effect. So the only stable solution is the trivial solution when electrons and soft photons, the number is 0. There are no electrons and no soft photons. However, when this injection compactness parameter is more than 3, there is the trivial solution is non-stable, and there is another solution which is stable, and it corresponds to the this growing nonlinearity, and it can saturate and at some level. So this is, let's say, okay. So we have this effect when the injection compactness is more than 3, and so what can be then the steady states below this line, which is like some analytical, we found some analytical condition for the between injection and magnetic compactness. The steady state solution, which is stable, is when you have when the system saturates on the level that the optical depth for gamma rays is less than unity, but still is not non-zero. And then above this line there is the steady state solution corresponds to the case when the optical depth is more than unity. So that would correspond to the case that you quench the gamma ray emission automatically. Automatically, it means that at the beginning you don't put any soft photons. This line corresponds to the energy density in created electron-positron pairs equal to the energy density in magnetic field. And above this line, this is more than unity. So this steady solution corresponds to the case when you load the system with pairs, electron-positron pairs. And here is the region in which the energy of the yes, this is more than this is explained. So basically, that's all I wanted to say about this, and maybe some applications to be thought. And so this is a very idealized situation. We didn't compute the spectra. Oh, one thing to say is that if we have the solution, if the system becomes optically thick for the for gamma rays that we do the analysis, the created electrons, of course, cool, and when they cool, they produce E2-2 spectrum. That this lower energy electrons produced by synchrotron emission soft photons with the spectral index standard of 0.5 spectral index. So it means there is more and more soft photons. So there it means that the opacity is even higher for higher gamma rays. So in other words, when for the given frequency of gamma rays that resonates, let's say, with this magnetic field, the optical depth starts to be more than unity, it automatically gives the optical depth for more than unity for also higher energy gamma rays. And so just it's not really application in a sense that we didn't compute the spectra, as I said, and there are many effects that can, just like roughly the numbers, if this is reasonable to think about this effect in some systems. So let's say there are ideas also discussed by Avi Levinson for some time ago, that you can accelerate particles very efficiently in the closest vicinity of these supermassive black holes, and those particles will emit TeV emission. So let's say something like dead quasars, where there is not that much accretion anymore, or soft photon fields, or even like accreting AGNs. So what is the magnetic field that we expect? Let's say roughly putting magnetic pressure close to the black hole equal to the accretion disk pressure, that would be the magnetic field expected. What lambda is the accretion parameter in a so accretion luminosity in Newton units, and this is mass of the black hole in 10 solar masses. So these are the energy of the gamma rays that would be involved in this process then. This is the injection that depends on the mass of the black hole and the luminosity of the gamma rays. And this is magnetic compactness. So looking at this and comparing to, let's say, the previous plot, we see that there is a possible quenching and efficient pair loading, but for the low accretion rate. So efficient pair loading mostly, so quenching requires in general high magnetic compactness, right? Because for low magnetic compactness, you have to have more, a lot of gamma rays injected to the system. But if the magnetic compactness is very low, even though the injection compactness is not that high, you can have this efficient pair loading of the system.
Do you have enough time to reach steady state? I mean,
yeah, when I checked, like when I was solving numerically the system, so it you have to have a cooling of the electrons much faster than they escape, right, for this process to operate.
Did you look for that?
Excuse me?
Did you look for that? I mean, what conditions would fulfill?
I was just checking very roughly, you know, plotting the evolution of the system, like time-dependent evolution, but with no application. As I said, I would hesitate to apply this kind of very simple system to some. It's just like to give, let's say, ideas about, you know, these two parameters for different systems. If it can be something interesting in this or not, right? So
pair annihilation is not considered here, right?
Excuse me?
Pair annihilation is not considered here, right?
No.
No, it's not. No, it's not.
At those densities. Shouldn't be considered.
Otherwise, you do not have some mistake.
So this is the, let's say in this plot summarized, this is the accretion rate in the Newton units. This is the critical luminosity. So this is the luminosity of the gamma ray at the frequency given here for different masses of the black hole. So that means that, for example, for the black hole of 10 to 6 solar masses, if we have, let's say, a system with black hole accreting 10 to 6 solar masses, accreting at 10 to minus 6 Eddington rate, then we should not expect the luminosity at, to detect anything above 10 GeV, above 10 to 48 per second. Roughly, that would mean that. And so this is the range of luminosities that can be really probed for these energies for the nearby objects, for all nearby galaxies. So this is.
What do you mean when you divide an electron on G square C?
Here?
Here.
Yeah. Yeah, this is just like it's just magnetic pressure equals the pressure of the accreting gas.
But it's not undimensional.
Okay, sorry, I just maybe this formula. I have to just look at this formula. But in general, this is correct. This maybe I was typing wrongly here.
It's fine, I think. Because it's energy density b square, and this is on the right is also L over r square.
Yeah, so
C
this
also
is of
energy
course,
density.
yeah, that would be because that is in Gauss units, right? So that should be in some units. Right? That should be like a square of Earth per centimeter instead.
Units of mass, like a battlefield.
Other sources, so let's say those galaxies, when we have the microgas magnetic field and the parsec scale radius. So The magnetic compactness is very low, so we don't expect really quenching, but we could have possibly efficient pair loading of such system if the injection is, let's say, more than 10 to 4 to 5 amps per second, which is anyway pretty high. The afterglows, here I don't think, like coming back to this question, that this analysis may not apply at all, because maybe there is not enough time to reach the steady state. Right? This is a very dynamical system. But let's say just plugging the numbers, Gauss magnetic field at 10 to 17 centimeters. So the gamma rays involved in the rest frame of the source is 30 GeV. Magnetic compactness is really high, and so if we have some luminosity, interesting luminosity, more than 10 to 42 erg per second, in the rest frame, at the rest frame photon energy is 30 GeV, that we could have a possible quenching of this gamma ray emission. So maybe we should not expect anything above, to observe from gamma ray burst, anything above 30 GeV in the rest frame. So observe would be like Doppler factor, like more. That's the one idea. And so as I said, this is so simplified that it's really just like to propose that there may be some interesting effects connected with this. How I imagine the application to the real system is basically the injection of high energy electrons to the turbulent system. So if we have this kind of situation with the magnetic field and some gamma rays, and due to nonlinear effects, you spontaneously absorb some part of the gamma ray emission, you inject the high energy particles to the system, and they cool. And I always think that just thinking about the system with the magnetic field where there is always cooling and no is too simplified, so you always have to take into account the stochastic acceleration of particles with the magnetic field, which is most likely turbulent, so you always have turbulent acceleration. And so some time ago, with Professor we gave solution for this momentum diffusion equation for any turbulent spectral, this is turbulent spectrum for any spectra of the turbulence and different cooling conditions, and injecting low or high energy electrons. So just like pointing out what could be, for example, in a system that are efficiently pair loaded due to this process. So you just inject, so this is the energy spectrum of the particles. These are the cases with no escape, when the escape is very inefficient. This is the for escape with different escape timescale, let's say. This is the cooling timescale and acceleration timescale. So always we inject high energy particles here, here, and then they cool, but they are also accelerated by the turbulence, magnetic turbulence. And of course, so this is, for example, the case when we have inverse Compton losses, Thomson and Klein-Shina, to acceleration timescale corresponding to the bond diffusion with different rates. And at the point when the acceleration equals the cooling, we have the Maxwellian, ultra-attenuated Maxwellian forms naturally. But the point is that when you inject particles at, so if you would inject particles at high energies, that would be the end of the story. If you inject at high energies, of course there is a cooling tail, which in this case deviates from E to -2 because of the Klein-Shina effect, and then you have this bound. And then it's, for example, for the very steep turbulence, so the acceleration is timescale independent of the energy, the same losses. You inject particles here, and these are the different spectrums that you can form. And this is with these escapes. So you have an ultra-attenuated Maxwellian, again for the bond diffusion, and the cooling tail. This is here just a synchrotron inverse contained Thomson regime, and the standard cooling tail E to -2. So it's very interesting to compare it, that sometimes when people talk about what is expected from the shock acceleration, that you have an ultra-relativistic Maxwellian due to shock-heated electrons, and then some parallel tail due to the diffuse shock acceleration. So basically, exactly the same spectra can be produced by completely different mechanisms. That's all.